Thanks very much. So, excellent talk about chaos. So, I'll be probably less about chaos. It is about mechanics, but with potential for chaos. I'll probably add in my conclusions, maybe. So, the outline of my talk is in those points, a brief introduction, there will be motivations for this work, then introduce a model based on Euler-Bernoulli beam, which is related to the main subject, how we model the system pulley and rope. Then introduce the suspension rope motor in a lift, which is moving, and present solution strategy to get some results, and eventually we will get some summary conclusions, hopefully. So thanks very much for staying for so long here. I hope that I will finish this by 3. I will do my best. Okay, so the introduction, why this research? It has been on my desk for some time, and we all know that steel wire ropes are still widely used. And despite new technologies, we've got belts and so on, in steel wire ropes will stay with us for some time. So what happens that in lift installations, they have a finite life and are subject to process of degradation. And that's because of the conditions which are happening. So the primary mechanism of degradation is bending. So when the rope goes over the pulley, it is subject to bending. There's a simple model here. There's a pulley or traction sheave, and there's a rope, there's a tension on both sides. So what happens when this rope is moving up and down, let's say up, then the curvature of the rope is changing from, okay, that's almost straight here at the, cut here, sorry. Died. I'm sorry.
You want the laser?
Yeah, okay, laser now, I think showing. Sorry, there's a laser is a bit weak.
I couldn't make it work.
Yeah, sorry. So the tension at the bottom is T. So when the rope is moving up, the curvature is changing from 0 or close to 0 to 1 over the sheave, when R is the radius of the sheave or pulley. So we are looking at the contact point here, potentially, not always, here at the horizontal line. That's slightly shifted by a small amount, depending on the stiffness of the rope. When the rope is very small stiffness, or we have a very flexible belt, that probably be almost negligible. However, for large diameter ropes, there is a transition period. So that's about it, how to identify and to quantify the changes of the stress, bending stress, going over the pulley. And that is a way to do it. Okay, now one aspect of this work is also that we know that there is a code requirement which states that we need to have at least 40 ratio between the diameter of the pulley and the diameter of the rope. So obviously the industry is quite aware of this for some time, and we know we apply it. And again, suspension ropes must meet BSEN 1, 2, 3, 85, 5, tensile strength. So bending is combined with tension as well, because that needs to be required and to take care of. Okay. All right, so let's go on. I'm sorry there will be some mathematics here, but I will quickly go through this. You don't need to really go deeply. It is in the paper, which is in proceedings. You can dip it later. But this is applied mechanics, quite fundamental in terms of mechanism of bending. So what I'm trying to do is to propose a simplified method to quantify the bending behavior of the rope, over the pulley, over the transition period, and later to use it possibly to many other applications. So the model which is proposed here is commonly used for wire ropes in dynamics, for example. Yeah, excuse me. Here is basically be statics. And the common model is referred to as Euler-Bernoulli model. Have you ever heard about Euler and Bernoulli? So again, those are two scientists who are Swiss of origin, and they developed this model in 1750, so quite a while ago. And this is referred to as an engineering beam model because it has been used since then widely in many applications, including Eiffel Tower, which was constructed and still standing. So it's quite an efficient model, and it can be used in many applications. For our needs, we will look how to apply this model to the bending of the rope over the sheave. Okay, it's better now. So again, this is the same. We are looking here. The mechanism of this is given via these two key parameters: curvature, which is changing from 0 to 1 over r, and the bending moment. Bending moment is produced by tension here. So there's a relationship between bending moment and curvature, and then there is this angle here, which is showing the shift of the contact point to point C from the horizontal line. Okay, this can be calculated using a relatively simple equation, which is here below. It is a differential equation. Assuming that we know the length of the rope, which is L here, over the arc. However, that's not always the case. So we can get some approximation from here. Once we do that, and we apply boundary conditions, so boundary conditions are what is the state at the ends here, we can then calculate bending stress in wires, in the rope or in the beam, because now our wire is actually a beam. And also we can calculate tensile stress. So when we combine those, we can design the entire system, including traction. Okay, so that's where we are. We call it global beam model. Okay. Now, in the suspension system, it is more complex situation. What happens? The system moves, and therefore, the length of the rope changes at speed. So what happens? This previous model doesn't apply directly because it does not take into account all conditions. And one key parameter here is velocity. So basically, though in play, we get centrifugal forces. Okay, that's a section of the rope here. I will not go into details. When you do, there's a free body diagram, and you take equilibrium of forces, moments, you get a couple of 4 equations, and from this we can calculate the curvature, tension. Now this length is unknown. You can also calculate length because we don't know the angle which is moving. The contact point is moving. It's not constant. It's not one point. So we can calculate this angle and also position of the section. It is Cartesian coordinates xy. So that's what are these equations about. Okay, they are nonlinear. However, they are called differential equations. So these two primes means differentiation with respect to s, which is the arc length, as you saw earlier on here. So that's s here, over here. Okay. No, okay, that's. Okay, so we've got differential equations. You think it is dynamic system. Not exactly. It is quasi-static, actually. Okay, so now we go. How to solve it? Okay, I will demonstrate the solution for a simple lift system, which is right here. That's a lift which has a 2-to-1 roping on the car side, 1-to-1 and the counterweight. And again, there's a sheave. So we've got the bending here over the sheave, and exaggerated bending of the rope is here. So again, we've got a shift of the contact point, and we're looking at the arc of the rope between 2 points, point A at the top and point B at the bottom. Here's a smaller pulley, which is a diverter pulley at the car, and there's a traction sheave. So the rope is being bent over the traction sheave and over the pulley. Okay, so not easy to solve the problem we had earlier on because it had a number of unknowns. First of all, we didn't know what is the length of the rope because it's slightly changing. Also, what we don't know is this angle contact point. Okay, so we cannot actually solve directly. That is a way we can non-dimensionalize the equations which I developed earlier on. very simply by using, for example, the arc dividing by the length. And what do we get out of this? When you have a, am I running out of time? No, okay. That's okay, so I'm getting there. So the domain of S is important here because that's integration domain. We had from 0 to L. L is unknown, it's function of time, problem. When we do this, we've got new S, and it is now from 0 to 1. Okay, and that makes us that mathematically we can solve the problem. Okay, so as I want to show you results now on one example here, very simple, for this rope, sheave system, and pulley and rope system at the car side. Okay, so the problem is what is referred to boundary value problem. Don't confuse with initial value problem, that's different. Boundary value problem is that we've got a system which has boundary conditions at the upper end, at the lower end, and the shape of the rope is described by the differential equation in terms of not time, but in terms of S. So we earlier on had simplified model where we assume that L is constant. There is a method to use boundary value problem solvers which are available when you apply initial guess. We know where to start with, we can solve the problem. And the first stage was and is to determine the initial guess using a very simple model when everything is known in terms of boundary and length of the rope. And now we use it into solver which is using a collocation method. That's a pretty standard model for BVP. And there are software tools which can do it. And we do it in MATLAB. And we can, this will be solved using for a set of parameters here on the right hand side. So for the lift, you've got mass of the car, because we are looking at the car side, okay? Mass, number of the ropes, mass of the ropes. In this example, there is this rope used, okay? 11 millimeter, 819S FC rope Draco. So 11 millimeter is the diameter of the rope. Then we've got some other parameters here, for example, speed. This solution will be dependent on speed, so that's what we need to bear in mind that there are centrifugal forces involved. Okay. One aspect which I want to mention here, and difficulty, is this parameter which is EI. You've seen these areas on what is EI? Does anyone know? Okay, that's bending stiffness. Okay, bending stiffness. So the issue of bending stiffness is a problem because steel wire rope bending stiffness is another big topic. However, we tried to get some numbers to get into the simulations. And that's what we did in the laboratory. We took the rope and we ran a vibration test. Because when you have a tension rope, there is a formula. You can calculate frequencies. Frequencies depend on the tension and on this parameter EI. So when you measure the frequency, you can calculate back the bending stiffness for this particular rope. And we did it. And we are using this value over here, 1.6 Newton meter squared. Okay, so that will be used in calculation. All right, so now we are getting there. So again, the example here is a simulation when the initial length of the rope is 2 meters and the lift is moving down at the speed 1.6 meter, and then it goes up to the length approximately 10 meters or so. Okay, so now when I run this, we get the actual results. Okay, and here it is. First of all, we calculate for the given set of data there the angle here. So that's the angle which we didn't know. That's here. This angle changes slightly at the top, at the bottom. At the top is decreasing slightly. At the bottom is increasing slightly. It's about 5 degrees at the top, at the sheave, and the bottom about 6 degrees. Small, but meaningful. It's meaningful. Okay, so now once we have that, we can get bending stress. Again, I'm using here global bending stress formula. for the wire. It is approximation. However, it is known, and it is from measurements. Klaus Ferrer, in his book, shows some experimental data. And they are not that far from those here for a given rope. Okay, so what happens here? The diagram shows stresses over the arc of the length from 0 to 10 meters. And that's at the beginning, which is the red line, and at the end of the moving system. Okay? So what we get, the stress is about here, the maximum stress on the beginning is for about 3.5 megapascal, 350 megapascal for the traction sheave, and about 400 megapascal for the other end, which is the pulley. At the beginning, at the end, pretty similar. Okay? So that gives us some quantification. That's meaningful. We know what the stresses are. Okay? All right, that's for the data set. I go back here. Still, okay. Okay, I should have mentioned that D to the ratio was okay in terms of standard, 51 and about 45. Now, what happens if we change it? So the change now, I go back, again, the same simulation, and that's what we get. So that's diagram showing slope during the travel. So that's the angle at the top, remember that. The blue line is for over 40. The red line is less than 40. It is approximately sort of 36 or so. And you see that there's a difference, quite substantial. So that's a traction sheave and diverted pulley, both, okay? So the same we'll see when we now calculate bending stress, okay? Bending stress. Again, there are couple of curves. Okay, that's at the beginning, that's at the end, and what we get at the for the less than 40, we get the red line. So we can see that stresses jump up. Almost there. So this is a simplified model which can be used to determine global behavior of the rope when it is moving and passing over the sheaves. It is based on a classical Bernoulli beam model, which has been used for many years. So we don't go deep into very complex contact mechanics, which you can find in many books. For example, Costello is a classical book, very complex equations. Now, we formulated boundary value problem, and we solve it numerically. You cannot solve it, unfortunately, analytically. We've got some results. Now, we saw that those results are intuitively okay. Actually, you compare them with Freyer's results. They are quite close to what is published in his book. Okay, and then the next stage is we can use this model in predicting or to estimate the lifetime of the ropes. So that's the next stage of the work. And there is another benefit, because, okay, then thanks to Professor Minangwa for his input into rope dynamics. Rope dynamics very often is modeled, the lift rope is modeled as a string. That's okay, okay? Assuming that they are highly tensioned. However, if the ropes are not highly tensioned, we would rather use bending model which accounts for bending stiffness. For example, for compensating ropes. Compensating ropes are less tensioned, and then probably the results will be more accurate. So again, thanks very much, and that's about it. Almost there.
Very good, well done, thank you. I'll allow one question before we wrap up.
Sorry.
Burning questions, or if I think people are ready to wrap up. So
I think we are there. So
just a comment. I mean, the slope angle seemed to me larger than I would have expected.
It depends on the type of the rope. If you take an 8mm rope, it will be very negligible. But if you take 11mm rope, and we know that in high-res application you use ropes are over 20mm, and I think you handle 20mm ropes. You take the 100mm rope and try to bend it. That's a bending stiffness. But it goes over sheave, you will see that there is transition period. Okay? So I think it lets us understand better mechanics of rope-sheave interaction.
Thank you.